First off, the first thing I want to make sure that you understand is that you do not need to memorize the periodic table. One will always be provided for you, and the one that I have up on the wall will always stay up on the wall. So there's no need to actually memorize the periodic table. The first thing I want to talk about in this video is element symbols. Typically, element symbols are 1 or 2 letters long, and the first letter must always be capitalized and the second letter must be lowercase. I will always count it wrong all year long if you capitalize both letters. So let me give you some examples. Sodium is Na. That's the correct way to write it. If you write sodium as Na and make this a capital letter but just smaller, that will always be counted wrong. Another example is bromine. Bromine is Br. Notice capital B, lowercase r. If you write bromine as Br that way, that will always be counted wrong. So the first letter must be capitalized and the second letter must be a lowercase letter. Typically the L's in element symbols sometimes are mistaken for I's, so many times you'll see me write an L as a cursive L. For example, chlorine, instead of writing Cl, I'll write it as Cl, so you don't mistake this for chlorine and iodine together, because that does kind of look like a Ci. So a lot of times you'll see me write L's as a cursive L, but you'll notice it's still a lowercase cursive L. The next thing I want to talk about is Dalton's atomic theory. You do need to memorize Dalton's atomic theory. There are 5 main points to Dalton's atomic theory. The first one is that elements are made up of tiny particles called atoms. The second one are that atoms of a given element are identical. And we know now that this is not true, and you'll see in the next video why, but it's pretty much because of something called isotopes. The third point in Dalton's atomic theories is that atoms of a given element are different than atoms of any other element. All that's saying is that an oxygen atom is different than a nitrogen atom or a fluorine atom. The fourth point is that atoms of an element can combine with atoms of other elements to form compounds, and we know that this is true based on things like water, where we have an element of oxygen combining with elements of hydrogen. And the last point in Dalton's atomic theory are that atoms are indivisible. This one we also know is not true. And the reason it's not true is because we know that atoms are made up of subatomic particles called protons, neutrons, and electrons that we'll get to in a later video. One of the first people that had input in on what the atom actually looked like was a guy named Thomson. What Thomson knew was that if you had an electric field, so let's call this an electric field here, electric fields are always charged negatively. If you shot a stream of atoms a parallel to that electric field, let's say if this was a detector over on this side, instead of that line of atoms ending up here, it actually ended up down here. And what he concluded from that was that the atoms were repelling that electric field. And so if the atoms were repelling that electric field, they must have some type of negative parts to them, and he called those electrons. And based on his experiment, he came up with a model of what the atom might look like then. And his atom is called the plum pudding model, and it's shown here. If he were alive today, it would probably be called something like the chocolate chip cookie model of the atom. And in his model, this plum pudding model of the atom, you could see he said the atom basically has this big spherical cloud of positive charge, and then it just has these electrons just spread throughout. They're not really moving or doing anything. They're just kind of in there all over the place. And this was really the first model of the atom. In an effort to try to prove that Thomson was correct, there was a guy named Rutherford that came next in the advancement of the atomic model. Rutherford was a master of coming up with really great experiments, and the experiment that he came up with I'll show you on the next slide here. Rutherford figured that if he shot radiation through an atom, and if Thomson was correct, most of the radiation would end up going right through the atom, and he should be able to detect that on a detector on the other side. But because the electrons were so small and spread throughout, most of the radiation would end up on this detector this way. And he came up with an experiment called the gold foil experiment to prove this true. And the idea was, if he proved it to be true, then Thomson's model was probably correct, that plum pudding model of the atom. Here is the gold foil experiment that Rutherford came up with. And you can see over here he had a source of alpha particles, and he was going to shoot those at a really, really thin piece of gold foil. And the thing that you're seeing here on the outside is just a detector to detect the radiation. So on that really, really thin piece of gold foil, if we could imagine that this is the gold foil, it would only be a few atoms thick. And there might be, here are all the electrons inside. If radiation came through, it should essentially miss most of those electrons and end up on the detector right on the other side of the gold foil. And he had a detector all around his gold foil. You could see the gold foil right here in the middle of the detector. And he went ahead and shot those alpha particles, or that radiation, and something really crazy happened. Not only did he see radiation on the other side of the gold foil, but there was some radiation that was actually shot back at him. And in Rutherford's paper, he describes this as shooting a cannonball at a piece of tissue paper and having pieces of the cannonball come flying back at you. So you can imagine he was pretty astounded by his experimental results, and he was then left to come up with what a new model of the atom would look like, because he knew at this point that Thomson's model was probably not correct. And what we learn from Rutherford's model is Rutherford said, you know what must be going on here is that instead of these little tiny electrons just throughout, there must be something pretty dense at the center of the atom. And that dense thing at the center of the atom must be positively charged. And as the radiation was coming, it probably hit that, and that's bounced off, and that's why he got radiation coming back at him, instead of going just through the atom. So while you would get still some radiation on the other side of that gold foil, there would be a significant amount, depending on the size of that nucleus, of radiation coming back at you. So Rutherford, while trying to set out to prove Thomson's model correct, actually disproved Thomson's plum pudding model, and Rutherford is the person who we hold responsible for coming up with the fact that there is a nucleus to the atom. And so that's what we learned from his experiment. And through Thomson, Rutherford, and a few other people who we're really not going to spend a lot of time on, we have determined now that there are 3 subatomic particles. Those 3 subatomic particles are the proton, which is positively charged, the neutron, which has no charge, and then the electron, which is negatively charged. As far as size goes, or mass goes, if we say that a proton weighs 1, then a neutron weighs about 1 also. Electrons are really, really teeny though. They're about 1/2000th of the size of the proton and the neutron. And so it's these two things, the proton and the neutron, that account for most of the mass of the atom. As far as a purpose, The proton's purpose is essentially to give the atom identity. The purpose of the neutron is to act like a nuclear glue and actually kind of glue all of those protons together in the nucleus of the atom. And the purpose of the electron is for giving us reactivity of different atoms. And you'll see later on that it's responsible for the reason why when sodium is thrown into water, it actually explodes.